You know that moment when you stumble across something so bizarre, so counterintuitive, it just sticks in your mind.
Hmm.
Today, we're plunging into one of those things, aerogel. You might not have encountered it firsthand, but trust me, its properties are genuinely remarkable.
Oh, definitely.
Our goal today, to understand the unique science behind this material and explore its truly, well, unbelievable capabilities.
Yeah.
Let's start with a question that really hooked me. What if a solid was almost entirely air and could make you completely waterproof?
That's the perfect way to begin, honestly, because the first thing you grapple with when you encounter aerogel is this fundamental paradox. It's a solid object you can hold,
Right.
yet it can be up to, what, 99% air? Just imagine that holding something that's practically empty space.
It's wild.
That's a key insight right there.
Yep.
Even what seems like nothing can have tangible form.
Exactly. And seeing it in action really drives that home.
Yeah.
You watch a small piece of aerogel and the slightest touch causes it to just disintegrate into a pile of dust.
Oof.
It looks as though you're handling a solidified wisp of smoke. It's crazy.
And that extreme fragility is, yeah, a defining characteristic of pure aerogel. But here's where it gets really interesting. What happens with that seemingly useless dust?
Okay.
You take that powder, apply it to a surface, even something as delicate as your own skin, and suddenly it becomes completely hydrophobic.
Wow.
Water simply rolls right off. This points to another key insight. The form of a material at the nanoscale can dramatically alter its macroscopic properties.
It's just mind-bending. The idea that this incredibly delicate dust can create a 100% waterproof barrier is so unexpected.
Totally.
And get this, that dust can also be reformed into new kinds of aerogel composites that aren't brittle anymore, almost like a foam.
Right, that's a huge step.
Think about what that could mean for protection in really challenging environments.
Precisely. That's where the true potential starts to become clear. Beyond just the novelty of being waterproofed by dust, these new, more robust forms could offer incredibly lightweight protection without sacrificing, well, maybe not strength, but durability.
Yeah, durability.
It raises an important question. How can we leverage this unusual transformation from fragile dust to durable composite?
Now, here's a little factoid that really surprised me. For something that's almost entirely air, aerogel apparently makes a really peculiar sound. Would you believe it's described as very metallic?
Huh. Metallic. That is odd.
It's the last sound you'd anticipate from something so airy, right?
Yeah, the metallic sound offers a fascinating clue about aerogel's inner structure, I suppose. Even though it's mostly air, the remaining solid framework, that network at the nanoscale,
The silica part.
yeah, the silica part, it vibrates in a way that produces that unexpected resonance. What's fascinating here is how that hidden architecture gives rise to such a surprising auditory property.
Okay, but let's move on to one of aerogel's most touted features.
Mm-hmm.
It's thermal insulation. I've seen it described as the lowest thermal conductive solid in existence,
Mm-hmm.
and even the best insulation in the universe. Those are pretty significant claims.
And they are largely justified. Aerogel's unique nanoporous structure, think of it like a sponge, but with holes so incredibly tiny, only a few billionths of a meter wide,
Nanometers, yeah.
is what gives it these exceptional insulating abilities. Air is already a poor conductor of heat, right?
Right.
But when you trap it within these minuscule pores, convection, the movement of heat through fluids, is almost entirely eliminated.
Okay.
This makes it incredibly difficult for heat to transfer through the material. This highlights a core concept. Trapping air in tiny, confined spaces is a remarkably effective way to block heat transfer.
And this isn't just some lab curiosity, right? We're talking about real-world applications in some of the most extreme places imaginable.
Oh, absolutely.
I know NASA uses this stuff to insulate spacecraft like the Mars rovers.
Yeah,
Which
exactly.
have to cope with absolute massive temperature swings.
The ability to maintain stable internal temperatures for sensitive electronics and scientific instruments in the face of such extreme external conditions is absolutely vital for those missions.
Makes sense.
It's a powerful testament to just how effective aerogel is as an insulator in the harshest environments.
So we've established it's mostly air, it's an incredible insulator, and in dust form, it's super water repellent.
Mm-hmm.
But then, the information throws in another twist. It can also exhibit hydrophilic characteristics. How on earth is that possible?
Right.
It seems completely contradictory.
It all boils down to the surface chemistry of the silica, that tiny 1% solid material we mentioned. Depending on how the aerogel is manufactured and treated, The surface can be engineered to either repel water, hydrophobic, or attract it, hydrophilic.
Ah, so it's tunable.
Exactly. So while the structure is key for its lightness and insulation, the surface chemistry dictates how it interacts with liquids. This reveals a powerful principle in material science. We can fine-tune a material's interaction with its environment by manipulating its surface at a molecular level.
That's amazing. The source even includes a demonstration of the hydrophobic nature. You sprinkle aerogel powder on water and it just floats.
Yeah, sits right on top.
It creates this clearly visible barrier on the surface. And then there's the submerged spoon that comes out completely dry. It's like some kind of science magic trick.
It really does have that magical quality. The hydrophobic aerogel creates a microscopic layer of air around the submerged object,
Like an air pocket.
preventing the water molecules from ever actually making contact. It's like having an invisible force field against water. What's fascinating here is how a material can manipulate the behavior of a liquid at such a fundamental level.
And then there's the demonstration of applying aerogel particles to skin. The video shows these perfectly round water droplets forming on the hand, but they're not actually touching the skin.
Right, they're hovering.
There's this layer of aerogel powder in between. It's even described as feeling like magic.
And that feeling of magic really underscores the unexpected nature of this material. You see water behaving in a way that completely defies our everyday experience. It's a powerful illustration of how manipulating materials at the nanoscale can lead to macroscopic properties that seem almost impossible. This raises an important question. What other seemingly impossible feats might be achievable through similar nanoengineering?
It makes you wonder, if this stuff is such an unbelievably good insulator used by NASA, no less, why aren't we seeing it everywhere here on Earth?
Yeah, that's the big question.
Why aren't our homes insulated with it? Why aren't we wearing aerogel jackets in the winter?
That's the crucial question, isn't it? And the source material points to the main reason. For a long time, the major hurdle with aerogel has been its extreme brittleness.
Ah, right, the dusk thing.
That initial demonstration of it just crumbling into dust shows you the practical problem. It's not exactly suitable for widespread use in construction or clothing if it falls apart with the slightest touch.
Yeah, okay.
This highlights a common challenge in material science. Exceptional properties often come with trade-offs, brittleness in this case.
Right, it sounds like you'd have to handle it with extreme care, which isn't very practical for everyday applications like building or apparel. But then the source introduces a potential game changer, combining aerogel with closed cell foam. What's the idea behind this?
Exactly. The innovation lies in embedding the aerogel within a more flexible and resilient matrix. Closed cell foams themselves are decent insulators.
Okay.
Due to their structure of countless tiny sealed air pockets, imagine lots of microscopic individual balloons.
Got it.
By integrating the aerogel into this foam structure, you get the superior insulation of the aerogel without its inherent fragility.
So, best of both worlds.
Kind of, yeah. The source mentions companies like Aurus Labs or Solarcore as being at the forefront of this kind of technology.
Right.
This suggests that combining materials with complementary properties can be a key strategy in overcoming individual limitations.
And they put this composite material through some pretty intense tests, right?
Yeah.
There's the flamethrower test
Oh.
on what looks like a sample of this foam aerogel stuff. Even though the shape of the foam seems to melt and distort under the incredible heat, it still provides significant insulation. Someone can actually touch the other side without getting burned.
That visual is incredibly compelling. You see this material exposed to intense heat, and while the outer layer is clearly affected, the heat just doesn't penetrate through.
Amazing.
It vividly demonstrates the dramatic difference in thermal conductivity compared to, regular materials. What's fascinating here is how the aerogel within the foam continues to function as an insulator even as the surrounding material degrades.
Then they go even further with liquid nitrogen. For anyone who isn't familiar, liquid nitrogen is unbelievably cold. We're talking around negative 196 degrees Celsius.
Minus 196 C. Yeah, that's cold.
They even show what happens to a bunch of parsley. When sprayed with it, it just shatters into frozen pieces. Pretty dramatic stuff.
It really emphasizes the extreme temperatures involved and the potential danger of direct contact. It would instantly cause severe frostbite to skin tissue.
Right. And then comes the truly remarkable part. They spray liquid nitrogen directly onto a person wearing this foam aerogel composite on their upper body, and they don't feel a thing.
Nothing.
They mentioned feeling a few stray droplets on their pants, like where it wasn't covered.
Yeah.
But the protected area is completely unaffected. That's an absolutely incredible demonstration of insulation against extreme cold.
It is. It powerfully illustrates the effectiveness of this modified aerogel in blocking the transfer of heat, or in this case, extreme cold. The fact that there's no sensation of the liquid nitrogen's temperature on the protected skin is quite astounding.
Just wow.
This really underscores the potential of this composite material for protecting against extreme temperatures.
And then they circle back to those amazing hydrophobic properties, but this time with a full body application. They literally cover someone from head to toe in powdered silica aerogel.
Yep.
It looks like they're being transformed into some kind of ghostly gray statue.
It's quite a striking visual transformation.
Yeah.
And then they submerge this completely covered person in water. The result, they remain completely dry.
Unbelievable.
The aerogel particles essentially create a microscopic barrier, preventing the water molecules from ever reaching the skin.
And they even point out that the person doesn't feel cold despite being fully submerged in water.
Right.
It seems like that layer of trapped air within the aerogel is also providing a degree of insulation against the water temperature.
That's a very likely explanation. The air trapped within the nanoporous aerogel structure would indeed act as an additional layer of insulation, further minimizing the transfer of heat away from the body and preventing that sensation of coldness.
So it works both ways, hot and cold.
Exactly. This highlights another benefit of aerogel's unique structure.
The underwater appearance is also really interesting. Apparently, the trapped air bubbles on the body create this thin, gray, shiny, silvery layer.
Like a sheen.
Yeah, that reflects the light from above, and you can even see these tiny air bubbles gently rising to the surface. Plus, the person reports feeling lighter in the water, presumably due to the buoyancy provided by all that trapped air.
All of these observations really paint a vivid picture of just how completely the aerogel modifies the interaction between the body and the water. It's not just about staying dry, it's about this fundamentally different sensory experience.
Yeah.
This raises an interesting thought. Could this property be harnessed for buoyancy aids or even specialized diving gear?
Possibly. And to top it all off, they even stand out in heavy rain, while completely covered in these hydrophobic aerogel particles and stay perfectly dry.
Just standing there.
It even looks like the rainwater doesn't even mix with the pool water because there's this distinct layer of aerogel in between. It's almost like creating a temporary, localized weather system.
It's a remarkable demonstration of the very strong hydrophobic effect. The aerogel creates such a robust barrier that even the force of falling rain isn't enough to penetrate it and mix with the water below.
Wild.
This underscores the potential for using this property in protective coatings and textiles.
Now, we spent a lot of time talking about the water-repelling kind, but there's also a water-attracting or hydrophilic type of aerogel.
The opposite, yeah.
This one doesn't push water away, it soaks it up. What's the story there?
As we touched on earlier, it's the surface chemistry that dictates this contrasting behavior. Hydrophilic aerogels have a surface that attracts water molecules,
Okay.
allowing them to be drawn into that vast nanoporous structure. This makes them incredibly useful in applications where precisely controlled moisture absorption is critical.
Like a desiccant, but superpowered.
Kind of, yeah. This illustrates the versatility of aerogel, where a fundamental structural similarity can lead to vastly different behaviors based on surface modifications.
And the source mentions some fascinating uses for this type of aerogel, like in museums to protect delicate artifacts,
Right.
and to safely store medicines by carefully regulating humidity levels. That makes perfect sense. It's like having a super absorbent sponge, but operating at a microscopic level.
Exactly. Its ability to absorb and retain moisture makes it ideal for creating stable and controlled environments for sensitive materials, preventing degradation caused by fluctuations in humidity. This highlights a less visually dramatic but equally important application of aerogel's unique properties.
Finally, the source delves into the optical properties of aerogel, which are also pretty unusual. Apparently, its nanopores are actually smaller than the wavelength of visible light.
Yeah, this part's cool.
What does that mean for how we see it?
This is where it gets really intriguing, because those tiny pores, just 20 to 40 nanometers across, are smaller than the wavelengths of visible light, which range from about 380 to 750 nanometers.
Tiny.
Certain wavelengths of light get scattered more than others. Shorter wavelengths, like blues, purples, and ultraviolet light, are scattered more strongly. This is a phenomenon called Rayleigh scattering, and it's the very same reason why the sky appears blue to us.
So that's why aerogel can sometimes appear to have a bluish tint. It's the same
No.
principle behind the blue sky. That's a fantastic connection.
Exactly.
And the source also mentions that because UV light has the shortest wavelengths in the visible spectrum, and even shorter, it gets scattered even more intensely, making aerogel appear opaque to UV radiation.
Correct. But what's particularly fascinating is what happens with longer wavelengths of light, like infrared.
Okay.
These longer wavelengths can pass right through the aerogel relatively unimpeded, making it appear surprisingly transparent to infrared light.
So it blocks UV but lets infrared through.
Pretty much, yeah. This effect is even more pronounced in bright sunlight. This opens up some intriguing possibilities for applications like specialized windows or sensors, maybe.
So to recap, we've taken a deep dive into this truly extraordinary material called aerogel. It's unbelievably light, mostly composed of air, and an exceptionally effective thermal insulator.
Hmm.
It can be both intensely water repellent and surprisingly absorbent depending on its specific type. And it even exhibits these peculiar optical properties, all thanks to its incredibly fine nanoscale structure.
Quite the resume.
It really brings us back to that initial question. How can a solid that's almost entirely air possess such a diverse and seemingly contradictory set of abilities?
It truly challenges our everyday intuitions about materials. By manipulating matter at the level of nanometers, we can engineer substances with properties that seem to defy the conventional rules of physics and chemistry at the macroscopic level.
Yeah.
It's a powerful reminder of the hidden potential that exists at the smallest scales.
Absolutely. It's one of those discoveries that makes you pause and really consider the immense potential that lies in understanding and engineering materials at such a fundamental level.
Definitely food for thought.
So as we conclude this deep dive into the fascinating world of aerogel, here's a final thought for you to ponder. Considering aerogel's remarkable properties and the exciting progress being made in overcoming its inherent brittleness, what other unexpected everyday applications might become possible in the future?
Hmm.
And what entirely new challenges might those applications bring with them?